Hello, everyone. Welcome to today's lecture. Today, we're going to talk about some applications of approximation in value space method that is covered in previous lecture. Our goal is to show the versatility of approximation in value space method and dynamic programming formulation, and also help you to prepare your term paper. So as a first application, we will show how multi-agent rollout can be applied to warehouse robots task planning problem. And this is a problem where it possesses the classical information pattern. And after that, Jameson will share with us his research where it's a similar kind of problem, but fundamentally different in the sense that it's a non-classical information pattern problem. After that, we would take a 15 minutes break. And after we came back, I will present approximation in value space applied to the so-called multiple object tracking problem, also known as data association problem. This is an important problem in computer vision community. So let's jump into the first application. Before going to the detail of practical application, I would do a short recap of multi-agent problems and multi-agent rollout. Multi-agent problems are a classical problem that dates back to the 1960s. And the key characteristic of the problem is that there are multiple agents collecting and sharing information selectively with each other and also with the environment or a computing cloud. Each agent applies its own decision sequentially in a discrete time based on the information available to that particular agent. So if we look at this picture, there is an environment or computing cloud, and some agents have access to this computing cloud and can also download information from the cloud, whereas others do not and can only share information between each other. It may select share information only collectively, only a subset of the information that is available to this particular agent. And what is important is that the overall situation is impacted by the collection of controls of all agents that is present in this environment. So there are major mathematical distinctions between problems that seems quite similar in this, that can be depicted by this figure. One type is known as classical information pattern, whereby all agents are fully cooperative, fully sharing, and never forgetting information. This type of problem we view as the easy case because it can be treated by dynamic programming. What do I mean by fully cooperative? I mean that they are all the agents that are present in the environment, they are in the same team and they work for the same goal, and they're sharing all the information that is available to each other. And this is an easy case. And the second case is called non-classical information pattern, where agents are partially sharing information and may even be antagonistic. This is difficult type of problem because it cannot be treated by dynamic programming. So that's a case where Jameson gonna share some ideas where specially designed multi-agent rollout or multi-agent type of algorithm can be applied. For the classical information pattern, conceptually, you can imagine there is a information cloud that is available, that is present, and every agent have access to, both in terms of uploading information, but also in terms of downloading information. This means, regardless how many agents are there in the environment, when each agent making decision, they all have the full picture of the situation. So they all have access to the information that are stored in the cloud, and every agent share fully its local information to the cloud. So in that sense, every agent make decision based on the common information, common collective information. In this case, this problem can be modeled as a discrete time system with state X and control U. And this state X is what I referred to a moment ago, this common picture of the overall situation. And the unique feature of the multi-agent problem is that the decision or control have M components, U1 until UM, and each component corresponding to one agent. And in the applications that covered in this lecture, actually every control component corresponds to a physical entity, corresponds to one robot. But in some other situations, agents may simply be metaphors. For example, the application that mentioned in earlier lecture, this robotic arm involving multiple joints, and you want to control the robotic arm, and each joint may be viewed as an agent, and collectively we want to make the control selection in order for the robotic arm to fulfill some, finish some operation. So for this classical information pattern problem, the theoretical framework is dynamic programming. Shortly, we will reformulate for faster computation. In the application I'm going to cover shortly, we will deal with exponential size of search or control space. Later, in Jamison's application, he will talk about both this computation in distributed fashion, but also more importantly, deal with this non-classical information pattern issues. All right, so for the warehouse robots path planning problem, we can consider this situation where there are multiple warehouse robots. They are moving in a common shared warehouse environment, and they have been equipped with some sensory or equipment that can share information, local sensory information with each other or with a cloud, so that each agent have the full picture of the overall situation. And we don't deal with the part about which agent assigned or which robot assigned to which target and so on. We assume all those assigned target, every robot has been assigned to a target, and they are certainly work as a team in order to finish the task as soon as possible. So in this situation, this problem can be modeled by this grid world representation, where in this particular figure, there are 3 agents, which are depicted by the solid circles. They can move at most in 4 different directions or standing still at each time instance, and with perfect vision. This is what we mean by a perfect classical information pattern, that every agent are fully aware of the overall situation. So the agents have been assigned to some target. For example, this particular agent shown by a red solid circle. The open circle with the same color is the target that this agent aims to reach. The objective is for all agents, all robots, to reach their respective targets in minimum time while avoiding collision with each other. For this problem, there is a simple heuristic, which is each agent follows the shortest path to their respective target, and while assuming all other agents are not present. And this is shown by the arrows in the figure. So starting from this multi-agent task finding problem inside the warehouse environment, we first abstract it to become a grid world representation. The next step is to go to the mathematical terms and derive the dynamic programming formulation for it. once we get to this stage, the state should be all the information that can be useful for control selection purpose. And in this case, it's the current position of all agents and their respective targets. And the control at each time instance, each agent has at most 5 choices. So their combination would be the actual control in this problem. And needless to say, it would grow exponentially with the number of agents, m. And we define the stage cost to be a function that is related to the number of collisions occurred at each time instance, as well as the number of targets reached at that time instance. So at this point, we obtain a dynamic programming problem, which in principle can be solved, but because of this exponential growth of control or search space, in fact, it cannot be solved. So at this point, do you have any questions? All right, everything's clear. As I mentioned earlier, at each time, we must select one out of at most 5 to the power m join moves. We'll show shortly, multi-agent rollout reduce the amount of search space to 5 times m while maintaining good properties. The key idea here is to break down the control selection process into a sequence of one agent at a time move selection. Shortly, I will show you videos, animations of multi-agent rollout calculation. I will show 3 different cases. So this is one case where agents are sort of spread out, and it so happened that the base heuristic, by simply following the base heuristic, every agent will reach their target position safely without collision. And this is a different case where simply by inspecting the figure, you can say, okay, in this region, it's a little bit more crowded, and quite likely there are going to be collision occur if they simply following the base heuristic. And the third case is more extreme, where there is only a narrow corridor for all agents to share if they follow the base heuristic. But we will show that by following multi-agent rollout, actually, in the case where base heuristic works well, multi-agent rollout can recover the base heuristic, whereas when base heuristic fails, multi-agent rollout manage to find feasible trajectories for all robots. In particular, you need to remember that multi-agent rollout is just like rollout, is an online algorithm that the calculation or computation need to be repeated at each stage. And each stage involve the following sequence of operations. Let's say this is, we call this agent 1, and this is agent 2, and this is agent 3. So each stage need to be repeat those 3 steps of operation. The first is to minimize Q factor associated with the first agent, while the following 2 agent 2 and 3 follow their base heuristic. And after this stage, agent 1 would complete its control selection, and we go to the next stage. Agent 2 perform minimization of Q factors, while agent 3 follow base heuristic. And then we proceed to the last stage, at which point agent 1 and 2 have selected their control at the present stage, and only agent 3 need to perform minimization over Q factors. All right. Let's go to the animation. For the first case, I will first show, as I mentioned a moment ago, this is the blue one is agent 1, and red one is agent 2, and green one is agent 3. And they have been assigned to some target. And a row here indicates the base heuristic, which is the shortest path, assuming other agents are not here. Well, first show how base heuristic perform. If you look at this figure, and you see actually by simply following the base heuristic, because it's all the agents are kind of spread out, so following base heuristic would not involve any collision. Let's see how well the multi-agent rollout perform. As I said, we first start with the first agent, and the first agent try all feasible actions, controls at the present stage. You can see it can go left, can go down, and can go right or up or stay still. And you try all 5 actions at the present stage, and the tail portion is constructed by following the base heuristic. Whereas for agent 2 and 3, they simply follow the base heuristic. Okay, so you can see among all the cases, the one in the here would have the smallest cost. Yeah, you can see this one have the smallest cost. Therefore, the first agent choose to move to the right at the present stage. And then we move on to the second agent, repeat the same procedure, although you notice that for second agent, move down is infeasible. So there are only 4 candidate control to try at the present stage. So after trying those 4 different actions, the tail portion is again constructed by base heuristic. And notice that here is a subtle difference. For agent 1, since the previous step have already calculated its present action, therefore agent 1 only follow the previously determined path, whereas agent 3 simply follow the base heuristic. Okay, so you can see here in this simulation, there is a collision incurred. And this is the point of running a simulation in real time, because for difficult layout or configuration, we cannot know a priori whether or not certain planned paths would cause collision. And running simulation, particularly cheap simulation, is easiest way to find out. So then we find out the action for the second agent, and we move on to the third agent and repeat similar procedure. Yes? Okay, so this is one step look at multi-agent rollout involving one step look at minimization, right? So we only want to, or we just branching out the control options for each agent for one step. But remember that if you look at here, this part is determined by the first step that involving calculation involving agent 1, but the tail portion is generated by base heuristic. So the dark blue is the one that the outcome of multi-agent rollout, whereas the tail portion is generated by Bayes heuristic. Okay, so, and you can see actually after all those calculations, we recovered the Bayes heuristic. So in the case where Bayes heuristic works well, multi-agent rollout will not mess it up. But typically, Bayes heuristic is not good enough. So that's where case 2 is. And if we look at case 2, okay, we can see there is a collision. Actually,
large force to respond to collisions. Okay?
Yeah.
In other words, here it's allowed to have collisions in the calculation, but the collisions incur a very large force and therefore are rejected from the optimization.
so if you look at here, every collision, there would be a cost, right? And all right, and 3 collisions in total. So now this time, our hope is by running multi-agent rollout through all those calculations, we can improve upon it. So for the first agent, again, we try 1, 2, 3, 4 different actions, whereas go left is not feasible, right? So we try 4 different actions, which is shown by this orange row, and the tail portion would be generated by Bayes heuristic. And agent 2 and 3 are simply following the Bayes heuristic. So at this point, we do not know a priori what the cost is going to be. And the easiest way is just run simulation and find out. All right. So we run simulation and actually see this one only involves 1 collision. So we already improved upon it. Recall that the initial Bayes heuristic have nearly 400 cost, and now we have 119. And that is smart because agent 1 tried to avoid this narrow path. So for agent 2, we repeat similar procedure. And note that for agent 1, the path is calculated by the first iteration, first step, first round of calculation, and agent 3 just follow the Bayes heuristic. So we notice, okay, at this point, this one still do not have collision. Fingers crossed that there's no collision. Okay, so at this point, we already find a feasible path for all agents. But let's carry on and follow the calculation. But if you want to stop early, I mean, this is one variation you can introduce, right? All right, so this is how multi-agent rollout operates. And remember, at each time instance, or there it involves, for each agent, it involves calculation that try out all its actions and then construct tail portion by Bayes heuristic, and the later agents simply follow the Bayes heuristic, and the preceding agents using the path computed in the previous calculation. And some of you in previous lecture have mentioned about the possibility of changing the order in which the agents operates or calculate their minimum Q factor. So here, first agent, second agent, last agent, it seems pretty random. How do I order them? So in principle, the formulation allow a change of order in which the agents are selecting their control at every stage. Remember, this calculation needs to be repeated at every stage. So let's go to the last case. Again, if we look at the current policy, it involves 2 collisions. And if we follow this default order, agent 1, 2, and 3, So remember that base heuristic have this cost 358. And okay, here must be a rounding error. You see, at this point, we have improved upon it. We get 191. But after this calculation, it's still 150, which means there is still cause collision involved. So what should we do? And one way, I mean, there are more principled ways that I'm going to touch upon later, but one way is simply randomly reshuffle the order in which the agents optimize their control. So if instead we optimize the control for the third agent first, you have 4 feasible actions. Try out all 4 different actions. All of a sudden, we see this is the case where no one get involved in collision. So apparently agent 3 is the troublemaker in the previous case. And we already find feasible paths for all agents. And we can carry on and finish the calculation, but you may just stop here at this point. I mean, it's a variation that you can decide. Okay. So let's get back to the slides. And actually, we perform tests of the algorithm and compare it with cooperative A star and introduced in David Silver's article in 2005. And in principle, cooperative A star basically compute one agent at a time as well, but it compute the entire path in a sequential manner and only at time 0. And what we find, and on contrary, multi-agent rollout, again, as I mentioned earlier, perform calculation at every stage. And in practice, we find multi-agent rollout always find feasible paths. And by which I mean we vary the number of agents present in the environment and perform multi-agent rollout. And if there is no feasible path find or fulfill some criteria, we reshuffle the order in which the agents optimize their control. And we find typically at most two reshuffle which suffice. After 2 reshuffle, entirely random, agents would find feasible actions, not for the entire path, but no collision for certain range. And also at a comparable cost. And this is the average cost between multi-agent rollout and cooperative A star among the feasible ones. So remember, for cooperative A star, when the number of agents grow to around 200, there's only 60% accurate success rate, whereas multi-agent rollout always success in our tests. Yeah.
Explain this figure on the left.
Yeah.
The one method succeeds 100% of the time, right? The other one, a lot lower. What is these blue squares and red squares?
So this red dots, yeah, this red dots are the success rate for multi-agent rollout in all the test cases. So in each test case, there are certain number of agents present in the environment. And for each case, we randomly generate 10 test examples and run both multi-agent rollout and cooperative A star. And we note that the success rate of cooperative A star drop when the number of agents increase, whereas multi-agent rollout in our tests always find feasible paths. We need to mention that when the situation is more challenging, there are more random reshuffle involved. Yes, please. Yeah. Yes. Yeah. Well, that's a fair question. What happened with CA star is that it calculate the entire path one agent at a time. More specifically, it's calculating in an environment. So if we look at a grid environment, it's a static environment, right? But what happened with cooperative A star is it attach a time tag to the physical environment. For example, you make copies of physical environment, but put a time tag on top of it. So you are searching paths in a three-dimensional space with 2 dimensions to be this 2D grid, and the third dimension to be the time. So searching in that environment is more costly than searching in this static environment. And more importantly, in this static environment, in our base heuristic, since we ignoring the presence of other agents, so it's a static environment, it's not changing. And what happened in practice is we can even compute optimal paths and store them offline. Whereas in this three-dimensional case, it's more challenging. And that's why we did not try out and compare it that way. Yes, please.
Yes, this slide. So on the left picture, where you said like multi-agent rollout always have 100% success rate.
Yeah.
Is it saying that you try every possible reshuffling order?
No. What I mean is, I think the change is the resolution is 10, which means we try 200, or I don't remember precisely, but several hundred of tests in total. And we find among the several hundred tests, multi-agent rollout always find feasible paths. And in practice, remember, multi-agent rollout need to operate it, this algorithm need to operate it at every time instance. So at every time instance, we carry out the calculation. And if the resulting solution do not incur collision among all the robots within certain distance, we accept it and move on to the next stage. And if there is immediate collision, then we reshuffle the order. And what we find is typically up to 2 reshuffle would suffice for all robots to not collide into each other within certain range. So it's not like enumerating all orders, because in this case, I said it scale well up to 200 agents. So if I try 200 different orders, it will not be possible. And in fact, there are more principled ways to define order, which I'm gonna get to shortly.
You can't try all possible orders. So you try one, doesn't work, you randomize the order, try the second one. But what's happened is that you only need 2, so to get a feasible solution in order to reach the feasible solution.
I have a follow-up question.
Yeah.
Which is when you said like you set up the testing instances, are you saying that you randomize the target position and the source position?
Yes. Yes. Yes,
Right.
yes, yes.
And just wanted to clarify what CA start self actually does. Like, is that just you start and you take one agent, move it, and then
Yeah.
everything has to move around where it has moved?
So more specifically, let's look at this figure. So for this agent, let's look at the first agent. The agent compute its shortest path, and then you construct a three-dimensional grid environment where in the first frame of the grid, there is this agent. Yes, precisely. And in the second frame, the agent is here and so on. So there is dynamic obstacle moving inside this three-dimensional grid environment. Whereas in our case, we just deal with this 2D environment, and we left for the simulation to sort out whether or not this strategy is a good one or a bad.
So your computation also gets like harder and harder as you go through more agents, or potentially even infeasible just because there's walls.
I mean, well, I think you are referring to corporate A star or referring to multi-agent rollout? Oh, so CA in our experience is that just like here, order matters, and recalculating is just a bit more expensive, or a lot more expensive. If the length is fairly long, you can imagine for long passes, it's certainly more expensive to search in long passes because this three-dimensional grid environment would be larger. Of course, there are more clever ways to keep track of this time stamps over the path, but nonetheless, searching in this two-dimensional grid is cheaper. And so let's take a quick look at the okay, it's here. So this is how the simulation for the test environment looks like. So we have up to 200 robots. And since the slot where potentially goods are delivered are known a priori, and the shelves are known a priori, we can compute shortest path between all shelf spots and delivery spots and store them. And because it's a static environment, this can be done. And then at every time instance for every agent, you don't need to calculate shortest path in real time. And that's one of the reasons it can be operated so efficiently. All right. So we have both paper and implementation can be found online. So we touch upon one variation of multi-agent rollout, whereas the reshuffling of the order would result in different but equivalent problem. What do I mean by that? So essentially, you can imagine for a new order, let's just look at the reversed order problem. Reversed order showing the animation. Then it's equivalent to this unfolded system dynamics where you first select the control of the last agent, and then you get to this state, and you select second to last control, and so on and so forth. So this would amount to an equivalent problem where, again, multi-agent rollout would amount to nominal rollout applied to this equivalent problem. Therefore, we can anticipate a large improvement because of Newton's method effect. And another thing that is important is multi-agent rollout allow parallel computing of Q factors. As you have seen in the animation that simultaneously we can generate the candidate solutions for a particular agent and run simulation and so on. They can be done simultaneously in parallel process if there are parallel computing unit available. And another thing is multiple base heuristic can be applied to enhance the performance. And all those ideas are independent of each other and can be combined. In textbook, there are additional material for both order optimization and some other additional variations. So any questions at this point?
To me, it feels like the first half of the way, like the M agent, the choices for M agent.
Yeah.
Then
Yes.
How do you parallelize this?
Well, what I mean by parallelization is that when you select the control for the first agent, let's say you have 5 different control candidates, then those 5 calculations, each involving simulation, and in order to find out the cost and so on, this part can be parallel, but not, you are exactly right. It cannot be parallel in terms of different agents, but that's something that Jameson gonna touch upon. Actually, in some cases, you can do that. So that's a perfect question to introduce the second application. All right. So let's get to multi-agent problem with non-classical information pattern.
Okay, so let's take a look at multi-agent problems with non-classical information patterns. Okay, so Yu Chao described briefly what a non-classical information pattern is. We saw the figure where each of the agents were connected to each other and also this computational cloud. So we're going to look at the cases where any of those links that you saw in the figure may or may not be there. So that's at a high level what a non-classical information pattern is. And I'll make it more specific what we actually mean here. So this is an outline of the section. First, we're going to review the multi-vehicle routing problem. I have a special formulation of it that we haven't quite seen in this course, but it's not complicated. So we're going to review that. And then we're going to look at a generalization of the multi-vehicle routing problem for non-classical information patterns. And then to approach solving these types of problems, we're going to use a distributed computing approach. And I suspect that none of you have ever seen anything related to distributed computing, except maybe if you've taken like an undergraduate operating systems course, and if you remember like the dining philosophers problem, it's all that kind of stuff. But I'm going to give you a very bare bones introduction to distributed computing, and it will be all the information that you need to understand the solutions that we're going to present. Okay, that leads us to this algorithm called decentralized multi-agent rollout, or DMAR. Then we're going to look at an experimental study, which looks at the impact of communication and coordination on performance. Then we're going to look at some physical real-world implementations. And lastly, we're going to discuss conclusions. We're not going to look at extensions, but I will give you a way to access the paper. Okay, so first is the multi-vehicle routing problem. I have this kind of special representation of it. So an instance looks like this. It's this rectangular grid in 2-dimensional space. It's a discretization of 2-dimensional space. There's a set of locations representing obstacles. In this picture, the black squares are obstacles, and these squares are not visitable by agents. They represent blockages in the network. There's also a set of agents that start at some initial position. So here I have agents represented by these little car drawings. The colors don't mean anything yet, but they will mean something later. But these represent the agents. And lastly, there's a set of task locations, which I have represented by these red X's. So to remind you, an instance is solved when each task is visited at least once by some agent. And the objective is to compute a set of trajectories that solve the instance such that the total number of vehicle movements is minimized. In principle, this can be treated directly with dynamic programming, although it will be very computationally complex. But this applies when we assume a classical information pattern. Are there any questions about this representation or this formulation of the vehicle routing problem? Okay. So I'm going to present to you a new problem called the unmapped vehicle routing problem with local constraints, which I have abbreviated as UMVRPL. In this generalization, the instance is not known a priori at all. We don't know anything about what the network looks like. We don't know the initial positions of the agents or the tasks or even where any obstacles are. Also, there is no centralized computational cloud. That thing is gone completely. And interagent communication and sensing is restricted to a sensing radius, which is a term I will use often, of k hops on the grid. In other words, an agent can only see within k hops of this grid. So this is clearly a non-classical information pattern. There is no computational cloud, and the communication between agents is restricted based on locality. However, if you bring the sensing radius up to infinity, then you just get the regular multi-vehicle routing problem back, because you have, as long as you have at least one agent, you can see the whole instance, and you can treat it as if it were just the multi-vehicle routing problem. And this type of problem, to our surprise, had not been considered in the literature until now. So as far as we know, we're the first ones to address this type of multi-vehicle routing problem. Are there any questions about this generalization? Yep.
Do we have specific new grid, or do we have just like arbitrary graph?
So I'm going to talk about grids because it's easier to say stuff about them, but in principle, our results could be extended to arbitrary graphs. Yep. So they can't communicate with each other unless they're within k-hops, that's right. So they can only see other agents that are within k-hops, and therefore they can only communicate with other agents within k-hops. Let me get to the computation part of that, because obviously some kind of computation has to be done here. Okay, so our approach is like this. So we're going to treat the problem with a dynamic programming-based decomposition. And for this, we're going to use a distributed computing approach. So the agents themselves are going to be processors with persistent memory. They're going to be capable of limited sensing, locomotion, and local communication. So in this problem, any computation that's performed at all must be done specifically by some agent with its limited knowledge and abilities. So no cloud. The strategy will be to generate sub-instances locally around agent clusters where information can be shared between agents. And these will form little small instances of MVRP, the classical problem. And then we'll apply approximate dynamic programming to these sub-instances individually and in parallel. And in the case where some tasks are not being covered by these clusters, there needs to be some sort of exploration aspect. So agents that end up not belonging to clusters will do a random search of the graph. So the applications of this are kind of interesting. So the first one I put is minefield disarmament. I see this as sort of an anti-war application. So in Europe today, and especially in Vietnam and locations where there have been wars in the past, there are still just thousands of landmines buried everywhere. And occasionally there are accidental deaths of people who step on these landmines still. And they can't be seen, obviously, because they're buried in the ground. But if you have a mine detector and you get close to the mine, like within 5 feet of it, you can detect that it's there and do something about it. But usually people don't carry those around. So that's an ideal application for this. Another application is post-disaster search and rescue. So if the landscape, for example, has been maybe devastated by some kind of disaster, and it no longer looks like it did in the past, like maybe it's a city or something, and there's been a large earthquake. And there's people that need rescuing, but you're not sure how to get to them or where they are. We have that kind of application in mind. Also, I have resource discovery and exploitation. Resources are not typically visible from the surface, but maybe some kind of like cave diving application. Not sure, but these are some ideas. Yes.
But in general, we don't have the number of tasks.
We don't know the number of tasks or what the landscape looks like. Yep, right. Okay, any other questions? Good. All right, so because we have this sort of distributed computing setup where each of the agents are processors, I wanted to cover some preliminaries related to distributed computing. So the first thing is the idea of a distributed model. A distributed model involves a collection of processors, and these processors have some sort of internal state, and they belong to this thing called a communication network. And it just looks like a graph. So here's an example. Here's processor P0, P1, and P2, and the links in this network represent communication channels between these processors. Processors can communicate with each other. Oh, I should mention this. A configuration is the collective states of all of the processors combined. Communication between processors is facilitated via message passing along ports. So a processor can communicate with a neighboring processor in the communication network simply by sending a message along these channels, which we call ports. There's this object called an event, which is characterized by either a computation, the sending of a message, or the receiving of a message, or anything that can update the state of an individual processor. And then a distributed algorithm is something that you can think of as like sort of like a transition function. It's an individual protocol that is assigned to a specific processor. And we start with some initial configuration. An event happens and we apply the distributed algorithm as the transition function to achieve the next configuration and so on. And this is how the process evolves. So here's an example of a distributed algorithm. I wanted to emphasize that it doesn't really look like your standard algorithm. So it's specifically for a processor P. So here's one. If you have a message in your buffer and your state is red, then set your state to green and forward messages along all of your ports. This is a very basic distributed algorithm. But how do we decide who gets to execute these individual protocols? This is done by some kind of scheduler. A scheduler will choose a processor to wake up, or we use the term activate. And when a processor activates, it just executes this algorithm that it has available to it. A special case of a scheduler, there's many different kinds, but a really easy scheduler to analyze is called a synchronous scheduler. In this, the processors repeatedly wake up and execute their common algorithm simultaneously. So this is divided into rounds. In a synchronous round, everybody wakes up, they execute their algorithm that they have on board, and then they go back to sleep, and then we repeat this. So everything is kind of nice and synchronized. So here's an example of this distributed algorithm being executed. Let's start with processor P0. Assume that its initial state is red and that it starts with a message in its buffer. So everybody wakes up. P0 has a message in its buffer by assumption, and its state is red. So it's going to do this. It's going to change its state to green, and it's going to forward a message along all ports. At the same time, P1 and P2 are going to wake up at the same time as P0, but this condition will not be true. Their state is red, but none of them have a message in their buffer. So they do nothing. So in the next round, they all wake up again. P0 has nothing to do because it has no messages in its buffer, so it just stays in its green state. But P1 and P2, well, this condition is true. They have a message in their buffer and they're red. So they change their state to green, forward messages along all ports, and then we arrive at this configuration. And after this configuration, there's no further progress that can be made because everybody's green. Does anyone have any questions about the distributed model or synchronous schedule?
You mentioned agent clusters in the previous slide.
Yes.
Is the size of the cluster fixed?
So I'm going to get to all of those nice details. This is just like a preliminary computation or as a preliminary slide to explain how our approach is going to work. Yeah. In some distributed models, yes, there could be some kind of message delay, but this model is very simple. We assume that in between rounds, all sent messages are received by the time of the next round. So in this algorithm, it does sort of a broadcast where it just sends the messages out along all ports. You might have a situation where a processor has like an ID and the algorithm can check against the ID and make decisions about a specific processor. Is that what you mean? Or in this algorithm, yes. But if they have IDs, then you can make special messages that only apply to certain processors. Yeah.
The burden message here kind of a buffer.
Yeah, we'll assume in this really simple model that once all of the messages are sent, they're all received and the buffer is empty before the next round begins. There are definitely other more complicated distributed models that don't make these kinds of assumptions.
So like a message lives in a buffer for one round?
Yes.
Okay.
Yep.
Whether it's something.
Yep. Anything else? Okay, so that's distributed computing. So here's our solution, decentralized multi-agent rollout. So DMAR is an iterative distributed algorithm that specifies state updates and message handling, leading to the collective behavior below. So oftentimes, a distributed algorithm is kind of difficult to read. It's difficult to say what the behavior of the system is going to look like just by looking at the algorithm itself. So often we describe them in terms of what is their collective behavior. And then it's sort of a challenge to prove that the distributed algorithm actually generates this behavior. So at a high level, I'm just going to explain what is the collective behavior that DMAR generates. And then we're going to look via an example at how it achieves this with their local algorithms. Okay, but first, I'm going to define something called a view. And the view of an agent A includes all instance information available within k-hops of the agent on the grid. So it's convenient to talk about views. Okay, are there any questions about these first 2 points?
Are you going to be assuming that the algorithm for each agent is going to be the same?
Yeah, so they're all what we call homogeneous, or homogeneous. Yeah, they all run the same algorithm all the time in parallel. Okay. Okay, so what is DMAR? So each iteration of DMAR repeats the following steps. So agents are going to self-organize locally into clusters of constant size around special agents called leaders. Agents within these clusters are going to form a tree communication network. So I explained what a communication network is. We're going to work with trees because it's convenient for broadcast. And the root of these trees will be the leader of that cluster. Yeah, okay, so I mentioned that the tree structure facilitates the flow of messages. And then if there are smaller clusters that are adjacent to each other, we're going to combine them into larger ones, because a source of suboptimality is if two clusters are sort of overlapping over the same tasks. They may send agents to try to take up these tasks without coordinating with each other. So the clusters are going to be independent, and we're going to try to make them somewhat big. Okay, so once these clusters are formed, for each cluster K, agents in K will route their views to the cluster leader. And then for each cluster K, the leader computes a set R of control sequences according to the multi-agent rollout algorithm, using some kind of greedy base policy. And this is applied over the assembled view information obtained from the previous step. So everybody communicates their view information. This somehow gets all aggregated at the leader, and the leader can treat then this individual cluster as a case of MVRP. So it has complete information within the cluster itself. Once these trajectories are computed, they get broadcast throughout the agent tree. And by the way, each agent has associated with it an ID, so it's easy for it to figure out which trajectory belongs to it. And then each agent moves along its assigned control trajectory, and once it finishes this, it unassigns itself from the cluster. It may be the case that some agents just end up not joining clusters at all because they're too far away from tasks or other agents. And in this case, they're going to generate a random trajectory of bounded length and follow it, searching for tasks. So this is a high-level overview of the collective behavior that the distributed algorithm is going to generate. Are there any questions about that? Yeah.
Step 5, set leaders assign control trajectory to each agent.
Yep.
But multi-agent rollout, each stage you assign one step. Here you mean that, like,
they're going to treat each cluster as its own little instance, and it's, yes, onto all agents within the cluster. So all of the stages will be contained in that cluster, and they will generate a full trajectory stage by stage.
so for example, two clusters, like two agents from different clusters, they cross up each other.
Yep.
And finish the task, but at the end, because they're too far, so they assign themselves on the original cluster and like.
Yes.
Two things, what do you mean by constant size?
So there is this parameter that I'm going to talk about. There's something that is going to prevent the clusters from getting too big, and it's going to be based on a constant parameter.
So bounded size.
Yes.
It is-
It's going to be a number that's independent on the network size, on the instance size. So it's just some constant that you pick, and it's usually quite small, like somewhere between 4 and 10.
And then just to make sure, like, you've got a leader and you've got some cluster, say that has like depth of 5 or something, it would take 5 rounds for each one.
Yeah, so it would, yeah, exactly.
So each guys are supposed to communicate and then break off.
So I'm leaving a lot of details out here, but there's a way to synchronize this whole thing where if so for example, if maybe one cluster is smaller than another cluster and it finishes its computation early, because of this parameter that we give it, they know exactly how long to wait, such that each agent is going to produce the exact same number of operations every time they execute this local algorithm. So there's a way to synchronize them like that, because we have this nice model. Yep.
So if they're talking about agent may assign itself from the cluster, so if you find the cluster dynamically forming.
Yes. 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 I'm gonna go into detail about how the clusters are formed. Anything else? Okay, so let's look at an example. So in this representation, the color is going to indicate cluster membership, but by default, everybody's gray. Gray just means you don't belong to a cluster at all. we're going to let k equal 2, so any agent can see 2 hops away from it. And so, for example, agent 2, its view will consist of this agent here, this agent here, this agent here, and this task here. So that's the view, and it can also see the obstacles in that view. Okay, so the way the cluster formation works is as follows. So any agent that can see a task at the beginning of this iteration of DMAR will raise a flag indicating so. So that's what these little flags represent. And then if you see, if an agent sees an agent that has its flag raised up, it will disqualify itself from becoming a leader if any such agent has a larger ID. So 1 can see 2, and 2 has its flag raised, but 1's ID is less than 2, so 1 becomes disqualified. 2 can see 3, and 3 has its flag raised, so 2 can disqualify himself from becoming a leader. And this leaves 1 unique leader per cluster. And the same thing is happening on the other side here. So this is a different cluster. Okay. All right. So once an initial leader is found, agents around these guys will start sort of iteratively appending themselves to the cluster. And there's also this other process where 2 adjacent clusters can be joined into a larger cluster. So I'll talk about that next. Okay, so 3 and 7 are our initial leaders here. And 2 is going to see 3 and see that 3 is in fact a leader and in a cluster. So it's going to append itself to 3. 4 likewise is going to append itself to 7 because it sees a leader. And 5 is also going to append itself to 7. But when this happens, this agent 8 sees 2 different clusters in its view. So once it notices this, it's going to send out these messages, and it's going to attempt to subsume these 2 clusters into a larger cluster where 8 is the leader. Okay, so it sends these messages, and then 3 and 7 accept the messages, so they join the purple cluster, but there's still these messages in transit. So, so going back, yep, so agent 1 joins this red cluster, which is in the process of dissolving, and we get this other thing where 6 now sees 2 agents in different clusters, so it also initiates this cluster join process and starts sending out these messages. But it might be the case that an agent like this one receives 2 of these join messages at the exact same time. If that's the case, it will just disregard one arbitrarily and just pick one somehow. So in this scenario, 4 is going to disregard the message from 6 and join the purple cluster. And this green cluster is still growing. It will send a message to agent 1. And this is the final cluster configuration. I could continue this process and eventually combine these clusters, but I've picked a size parameter that prohibits this. So this is an example of a multi-cluster instance.
Or why is 4 not joining 6?
4 not joining 6. Oh, so it could have joined 6. It received a message at the same time from 2 different clusters, and it just picked one of them to join.
Arbitrary.
Yep, arbitrarily.
Elaborate how like K, like 2 hops.
Yeah.
Stops it from being like 1 check.
So this guy can only see this limited area around him, and likewise everybody else.
9 blocks.
9 is actually too far away to see anything. There's nothing within 2 hops of 9.
You can only see the excluding itself. You can only see like 8 cells.
It has a radius of 2 hops, so it can go 1, 2, and then that's it. So its radius looks like this.
Well, it's not
Sorry.
like if it was like if there's 12 blocks.
Yeah, so it's something like k squared times pi approximately. That's the area. Yeah. Okay. Yep. Yep. Right. So I'm sort of leaving some details out of the algorithm. The reason is in the algorithm, it's not meant to do so at this time. So I haven't described this whole thing like in complete detail, but at this, basically at this phase of the algorithm, it's not looking to join a new cluster. Or sorry, it's not looking to join two clusters is what I mean. So at this part of the algorithm, it's just receiving two messages at the same time and disregarding them. I'm trying to keep this like as abstract as I can and hide as many details as possible because the algorithm looks complicated. Yeah. In this case, we don't let it block vision, but in the extensions of our paper, like in the appendix, we consider line of sight based view definitions and look at how those affect the performance overall. No diagonal hops. Are there any other questions? Okay. So the point is, I guess the takeaway from like understanding this is these clusters get formed locally around tasks via this leader election process. And sometimes clusters can be combined into bigger ones. But what you end up with is this collection of clusters at the end of this process. That's the takeaway. Okay. So once these clusters are formed, this is basically the rest of the algorithm. Agents in these clusters will pass their view information through these tree edges, and they will aggregate a complete map of the cluster at the leader, in this case 8 and 6. And then the leader applies multi-agent rollout to the cluster map, and then broadcasts these trajectories throughout the tree. Then agents follow these trajectories, and agents not in a cluster will perform a random walk. So I mentioned that agent 9 was too far away to join a cluster, so it remains gray. So this agent here would start moving randomly, whereas these agents would move according to the trajectories computed by their respective leaders. Okay, so that is the algorithm at a high level. So what are the connections to approximate dynamic programming? So here's some observations. So I mentioned that when K is infinity, a single cluster is formed and rollout is performed with respect to the entire instance by a single processor. So if K is infinite, only one cluster is formed and the leader will perform multi-agent rollout on it. And it'll just be the same thing as MVRP. But reducing K approximates the rollout structure by decomposing the instance. And the aggregation of these smaller solutions yields a solution to the full instance that approximates the rollout solution. That's the idea. And even when these clusters are small, using multi-agent rollout as opposed to rollout is still an imperative because of this curse of dimensionality. Even if you have like 10 agents or something, it greatly increases the amount of computation necessary unless you use this one at a time approach. And then some notes on distributed computing. Distributed algorithms can be challenging to design and also challenging to describe. They rely on these primitives such as leader election and message passing. And sometimes the communication networks are dynamic, as somebody pointed out. In this case, they change over time. And proving that a distributed algorithm produces a specific collective behavior can be also challenging due to these things called deadlocks and invalid configuration. An invalid configuration is some kind of configuration that you shouldn't be able to reach. For example, if you have like 5 agents in a cluster and they're nowhere near each other, this is some kind of invalid configuration. So you have to prove that the algorithm doesn't generate these kinds of configurations. And also there's this idea of a deadlock where the algorithm can't make any further progress before it's solved the problem. In addition, randomized elements, as this algorithm has, they also require careful analysis. Okay, so are there any questions about this slide?
I wonder, like each cluster is considered MVRP, like normal MVRP problem. when you do the simulations, like it could crash into another agent, another cluster.
So in this model, we assume that agents can co-locate, but we're going to, again, at extensions, look at what happens if they can't be in the same place at the same time. But yeah, so, and I think another part of your point was, here's two clusters. Suppose they both like overlapped a task. They're both going to try to solve that same task. So it's kind of a source of suboptimality. So you wouldn't have that if K was infinity. Okay. All right, so next we're going to look at this experimental study that looks at the impact of communication and coordination on performance. So the goal of this study is as follows. We want to quantify the amount of local information necessary for DMAR to produce good solutions. But I mentioned that this problem has not yet been considered in the literature, so there's no benchmarks for it. So to address this, we consider a greedy strategy that we call the base policy. It's similar to DMAR, except for it doesn't use multi-agent rollout. It just uses a greedy nearest task type of heuristic. So this base policy involves no coordination, and it can be applied to this UMVRPL case because agents can just sort of move around the map, and if they happen to see a task, they can just go for it. So eventually, provided all tasks are reachable, this greedy algorithm will solve the instance. We're going to look at the role of coordination and communication. So specifically, we want to know how large must the sensing radius K be such that DMAR outperforms this base policy. So here's the experimental design. We're going to consider 8 classes of grids. We're going to look at 10 by 10s, 20 by 20s, all the way up to 80 by 80. And then for each class, we're going to consider 3 different agent to task ratios. So same number of agents and tasks, 2 to 1 and 1 to 2. Then for each of these size and ratio combinations, we're going to uniformly distribute obstacles over 20% of the nodes, and we're going to repeat this 10 times. So we're going to make a lot of different instances. And then for each of these instances generated, we distribute the agents uniformly and execute DMAR and the base policy 10 times for each of these over several fixed K values. So we're going to vary the sensing radius over all of these aggregated instances. Then for each run, we're going to record the total number of vehicle movements as well as wall clock running times, but we're not going to focus on this part, just vehicle movements. The total number of simulations, so there's a lot of combinations here. So like the total number of actual simulations ended up being more than 50,000 for the primary study. Just wanted to point that out. Okay, are there any questions about this slide before I continue? All right, yep. So in this algorithm, all of the clusters are independent, so there's no communication between them. However, you could potentially extend this to have inter-cluster communication, which might be interesting.
Follow up that, like, you were talking about once the cluster are formed, there's no combination in the cluster.
That's correct, yeah.
Okay.
But maybe you could. I haven't tried it. Okay. So
Classes can join, then break up because agents drift away.
Yeah.
Perhaps to do some task that's far away. Doesn't want to carry that cluster together.
yeah, so we thought about like, so in this algorithm, once all of the tasks in a cluster are solved, the agents could be anywhere within that cluster. They might be like disconnected from each other, meaning that there's no way to, like, if you're just hopping like K hops, you might not be able to get any more from one agent to another. So to address this, the clusters just sort of dissolve and the process repeats again. But there is this idea of maintaining persistent clusters that try to like blanket an area. We haven't done this, but that has some distributed computing challenges associated with it to try to keep them all within k-hops, like k-hops of each other. Okay.
Wait, but I have one more question. Like when you design the baseline for this one, you're saying that you first have to let all the agents to randomly screen the map, right? And then if it sees like task within the k-hop
Yeah.
division, it does it. So I guess the performance of this baseline also is really impacted by this like search strategy.
Yeah, okay, that's another good point. You could pick possibly better exploration strategies. Like one that we thought of was there's another random search strategy called a random waypoint, where you pick a direction and a distance each uniformly at random. So instead of kind of a Brownian kind of random movement, you get this kind of zigzaggy movement, and maybe that's better. We don't know. Yeah. Mm-hmm.
So each cluster only swap time for the task efficiency, right?
Yes.
Not the other one.
Correct. Yeah.
So it's possible that if some task is beyond the initial k-hop, it never gets solved, or is there a second iteration where the
So because, okay, one of the reasons we picked like the simple random walk, even though it might not seem very intelligent, it's because it's quite easy to analyze. So I don't have our theorems displayed on this on these slides, but we have theorems that show that the expected number of rounds before DMAR can solve all tasks is bounded. And also the probability that some task remains unsolved or uncompleted in the limit goes to 0 as time goes to infinity. So that's a part of our theoretical results, but we figured you guys didn't want to see any math right now. So, so I didn't put it on the slide. Okay, but so that's the theory about DMAR and its properties, and then we also show stuff like it doesn't deadlock and you don't get invalid configurations and things like this. Okay, so back to the study. Okay, so let's look at the results. So let me help you read this figure. So here's a representative sample. This is just looking at the 80 by 80 grids, but the other plots look like this. So on the horizontal axis is the view radius. So here on this part of the axis, the view radius is small, and then it gets bigger as you move to the right. On this vertical axis is the total number of moves. For this talk, let's ignore this axis, and we're going to focus on these two curves right here. So the blue curve represents the total number of movements incurred by DMAR for a fixed radius value, and this is averaged over thousands of instances. And the red curve is the same thing, but for the base policy. So as K increases, as you might expect, performance, yeah, okay. The performance of DMAR gets better and better because this sort of represents the amount of local information available. So the bigger this view radius, the fewer number of movements computed by DMAR, and also the base policy too. But it should be the base policy sort of independent of this view radius. Well, no, actually it's not, because the bigger the view radius, the more likely you're going to see a task that's like maybe 10 hops away, and you can just beeline towards it, right? So, okay, so the base policy is not decoupled from the view radius. Okay. At some point, we found is as you increase this radius, there is this special radius, which we call the critical radius, K star. At this radius, DMAR starts to consistently outperform the base policy. So it's at this point here, they're sort of the same, more or less. And then at this point, you start to see a divergence where the cost of the base of DMAR starts to get lower than the cost of the base policy. So we call this the critical radius. And then just beyond K star, is this thing that we call the effective range, which is represented by this brown shaded area. In the effective range, you can look at the costs incurred by both DMAR and the base policy and compare them to when the radius is really big. So because of the way we've distributed agents across the grid, when the radius gets close to like 16 or 20 or so, it ends up sort of subsuming the whole grid. Like everybody can see everything. Remember, this is an 80 by 80, these are 80 by 80 grids. If the view radius is 16, then just about everything can be seen. But to measure the amount of decentralization, we have this other plot here. So on the horizontal axis, we still have the radius size, but on the vertical axis, we have the number of clusters generated on average. So in this effective range, compared to the largest radii we considered, we see a factor of 2 to 4 detriment in the cost of DMAR, while still there is a reasonable amount of decentralization happening. There's still a lot of different clusters being generated. So what we're seeing is things are scalable. Like the detriment to the cost for having this restricted view is like a constant factor than if you could see the whole map, for example. So that's what this is showing. Are there any questions about these plots? Yeah.
Cluster count for,
okay, yeah, okay. So the only difference between the base policy and DMAR, like it still forms these clusters and communicates map information around. But when it comes to actually computing the trajectories within that cluster, instead of multi-agent rollout, it just uses the base policy. Yeah. You could have another option for a base policy would be to not generate clusters at all and just move around randomly. I suspect it would perform even worse because worse than the cluster-based policy. Yeah.
what is the benefit of getting to a cluster groups and do base policy?
Because if you're sharing view information, you might be able to see more than if you were just using your own local radius. But I mean, we haven't done any experimental studies on this, but it's just sort of a hypothesis. Yeah. Both. So within the cluster, they're just acting greedily for the base policy. Yeah.
So are the 4 agents going to move for the task that closest to that?
Yes.
Individually.
Yes.
So even that might mean that one of them move for the same.
Say that last part again.
Even that might mean one of them move for the same.
Correct. Yes.
So wouldn't they anyway do that if they don't get into a cluster? Except the case, of course, if one of them can see something and the rest cannot see anything.
Right. So sorry, what was the question?
So I'm saying that in the case where each of them can spot something before getting into a cluster.
Yeah.
They will anyway.
Oh, the cluster, the fact that they're in a cluster won't really make a difference. That's right. Yeah. I can just foresee possibly some sort of like edge case where sometimes an agent can see more. I don't expect that it will affect things all that much, but if anything, it would perform a little bit worse. But I don't know. Yep. Okay, so this is a representative sample, the 80 by 80 grids. Let's look at the aggregated results. So this plot plots on the horizontal axis the number of nodes in all of the networks, and the vertical axis represents the critical radii. So for a 10 by 10 network, we got this sample as the critical radius on average, and then for 20 squared, this was the average critical radius, and so on. So if n is the number of nodes in the network, then we found that the critical radii grow proportionally to log star of n. So this is not log of n, this is the iterative log function. if you take a number, say n, the iterative log function returns the amount of time, the number of times you need to apply the regular log function until n gets less than 1. That's the iterative log function. And what's interesting about this is that log star of n is at most 5 for any n that's less than or equal to this astronomically big number. This is an incredibly slow growing function. What this means is that the critical radius is basically just a small constant for any relevant instance. It's just constant. It doesn't matter how big the network is. So that's what this is showing. Are there any questions about this? Oh, I have some other like slow growing functions here just to show you how like slow log star grows.
The number of nodes, is it the number of agents in one cluster or what?
It's the size of the network, like the whole instance that you don't know about. So like in this example, the number of nodes, oh, well, it's just like, okay, it's all of these squares. So for the 80 by 80 case, the number of nodes is 80 squared. Yeah. Any other questions?
It also has to do with the number of agents, right?
Yeah, like I guess, yeah, so if it was very dense or very sparse, then that matters. At least so in the way we've distributed these agents, and by the way, I don't think I wrote this anywhere, but if you have an 80 by 80 grid, then we put 80 agents down. So it's always square root of n agents in this experiment. Okay. We also did physical implementations of this algorithm. We used the Robotarium platform at Georgia Tech. I'm not sure if you've ever heard of this before, but it's basically this citation generator for the scientists at Georgia Tech. You give some code that you programmed yourself to a server. It does some safety checks, and then these little robots that are about the size of cell phones just sort of run out and perform your algorithm in this arena. And there's nobody here monitoring it. It's all just automated. I'll show you some video. It's kind of fun. Okay, so this is a physical implementation. Planning by these robots occurs in discrete space and time, but once these controls are computed, they're mapped to this continuous space velocity vector, and a new position is moved to with actuators. So there's some kind of function that maps discrete controls to some physical actuation. That's how this is implemented. The simulations were repeated with these varying sensing radii. So these are real valued numbers now. So we did 20 centimeters, 40 centimeters, 60 and 80. I didn't put it here, but we also did infinite just to see how much of a difference it would make. And the results reflected our discrete simulations in terms of competing with the base policy. So I'll show you a video. Okay, so I have this sped up 20 times because they're a little bit slow, but let me pause it. So these little rectangles or quadrilaterals represent obstacles. The little circles represent tasks, and the robots are obviously the agents. And when they form clusters, you'll see these shapes that are overlaid on the agents. Like, for example, this guy has a star. It's a little bit hard to see, but this guy also has a star. And these shapes are going to indicate cluster membership. So this is just a little arena, and there's this overhead projector that is beaming down these shapes onto the floor. And then these are little robots. So I have 3 instances in here. It takes about 1.5 minutes to watch this video, but they go through and execute DMAR, and eventually they solve all the tasks after they form clusters over and over again. I love watching them run out onto the arena. It's my favorite part. So let me pause it. Yeah, so here's a cluster here. These guys have this little circle associated with them. Here's another one here. And this is another one here, and this guy's by himself. These the shapes indicate the cluster membership.
Sound effect. Anyway, it's a fast. Well,
That would be, that sounds like a great idea. Okay, so there's some example simulations for you. So let me wrap this up. So here are the conclusions of the study. So the conceptual framework coupling classical and non-classical information patterns is as follows. We explore the interface between classical and non-classical information patterns by adapting methods used in the classical setting to the non-classical setting. This led to the concept of clustering and applying multi-agent decision making in a decentralized and parallel way. The critical quantity connecting the classical versus non-classical information patterns is the sensing radius. And what can we say about the sensing radius? Choosing a sensing radius in the effective range allows for greatly increased scalability at a small detriment to solution costs. So one thing that I didn't emphasize much is that in these distributed systems, because all of the computation is spread out throughout the processors, there's essentially, depending on your algorithm, there could be like infinite scalability. So these clusters generated are bounded by a constant, which is given by a parameter. So each agent only ever has to remember a constant amount of stuff and do a constant amount of computation. So this thing is just going to scale infinitely, no matter how many agents you have. What else can we say? Because of this log star growth of the critical sensing radius, you can choose a good sensing radius without knowing anything about the size of the network. It doesn't matter. So truly, the instance can be unknown and you can handle it. Then the sensing radius must be large enough for good solutions, but not so large that agents can just see the whole network, which is a principal conclusion. And then lastly, I have this applicability conclusion, which says that our approach is highly scalable and is conceptually adaptable to continuous space and is robust to sensor noise, which augments its real-world applicability. That's it. So this paper is going to appear in the proceedings of the 23rd International Conference on Autonomous Agents and Multi-Agent Systems, or AMAS 2024. I don't have the ACM link yet, but if you want to look at the archive version of the paper, you can take the picture of this QR code.
I have a question with respect to the sensing radius. Like at least for the spiders and flies,
yeah,
you kind of do simulations and make the best choice among this stage, and then all the spiders move a little bit. Like when the spiders spread really out, like for example, like out of the K hops, are you still able to like are they gonna see what each other sees? Because like it seems like K hops is the limit for communication.
Well, actually, no. So the limit for communication is based on these agent trees, because you can have a chain of agents and each of them can be with K hops of them. And an agent on one end can communicate with an agent on the other end just by message passing through this chain.
So their communication between each other is not going to be bounded by the physical like distance. Cluster.
Well, it takes some time for the messages to reach from one side of the cluster to the other, but it happens eventually and in bounded time. Are there any other questions about anything that I've showed here?
Question. make a comment, but it just came to my mind that a turn tape, spiders and flies, the sensing radius, less than infinity. They could turn tape.
Oh, yeah, so a stochastic extension of this. I'm not exactly sure how that would be done, but that's a potential avenue for future work.
Maybe the tasks are around.
Yep. Maybe according to some known distribution. Okay, well, if you have any questions that come to you later, you can always ask me. Thank you. All right, ready?
All right, guys, let's jump into the last application, which is approximation in value space applied to multiple object tracking, or known as data association problem. This is a wildly different problem than the previous two, but hopefully I will convince you that the methodology introduced in this course are equally relevant and equally effective. But before we go to the application, I will first remind you the general discrete optimization problem that has been discussed in previous lecture. This general discrete optimization problem is about minimize a function g of u subject to some set where u belongs to. And we assume that each solution u have n components, u0 until un minus 1. And we can view each component as a stage of control. So the problem can be viewed as a finite horizon optimal control problem that can be treated exactly in principle by dynamic programming, whereby starting from artificial initial state, we select the first component of control and view as state this new single selected control component, and move on to the next stage by selecting the second component. So the state at stage K would be the partial solution constructed in the previous stage. You're familiar with this picture because you have been dealing with traveling salesman problem in your homework. So there are no costs in the intermediate stage until at the very end of the horizon, we have a cost g of u, which is the cost of which would be viewed as terminal cost in the context of optimal control. Of course, this formulation typically makes little sense to solve for us to solve the problem exactly, but often it makes a lot of sense for approximate dynamic programming or approximation in value space methodology applied to address discrete optimization problem. In particular, for this problem, if we want to solve it by dynamic programming, we start with this non-function g of u, which in the context of dynamic programming, it would be the optimal cost of the terminal stage, the last stage, which we denote by standard notation Jn star of xn, which would equal to the terminal cost g of xn, where xn is the complete solution for all xn. And recall now xn is the complete control u, the control sequence. It must belong to this set. And for k from 0 to n minus 1, we perform the standard dynamic programming calculation by minimizing all the available control at a particular state. And typically we see a stage cost and optimal cost of future stage, but now that term is gone because, as I mentioned earlier, the intermediate stage costs are 0. And xuk, this control constraint set, of course, depending on the problem, need to be constructed or defined suitably. After we obtain all J star, we can construct the optimal solution by forward calculation that one component at a time start with U0 star by minimizing over J star of 1 and so on and so forth. And eventually we construct the sequence. But as you have experienced in the traveling salesman problem, if you solve it exactly by dynamic programming, this would mean that start with the last stage, which is the complete trajectory, the complete tour of the traveling salesman problem. You enumerate all of them and calculating backward, and it really makes little sense. So what happened in reality is if we want to solve it using approximation in value space, we use some cost approximation, J tilde K plus 1 in place of J star, and performing this forward calculation by starting from the artificial state, set respective component to be U tilde of K at K stage by minimizing over this expression where this JK plus 1 tilde is something we construct or define or even calculate in real time. So how is this relevant to multi-object tracking problem? If we look at this academic example where we have, let's say, a video stream, and this video stream has 3 frames, and we have 3 objects or 3 people. They are moving in this common environment. And what we like to do is we want to match the same person over various frames. So this is precisely what multiple object tracking problem aim to do, is try to match the same object over various frames. And as you may see, if we list all the objects in one particular frame and do this frame after frame, then matching the same person over various frame would somewhat, loosely speaking, look like this matching over this layered graph. And this problem is highly non-trivial because of various challenges. And in practice, there can be additional challenge, but let's just assume that every object in various frame has been identified and put in box in clearly drawn box. Then there are still other challenges like occlusion. For example, in this particular case, this gentleman is blocked in part by this lady. Also change in object appearance. For example, this lady in this frame and this frame look, I mean, from our view, it's quite obvious it's the same person, but for computer, it's different. And also there are pressing real-time computation constraints because typically we want to do this matching in real time, and typically this frame coming in a very fast speed, and we want to conclude the calculation in real time or as soon as possible. And it's an important problem with a lot of applications. For example, both pedestrian or vehicle monitoring, robotics application, consumer analytics. For example, in a store that the business owner in this big store, the business owner would like to know, okay, what group of people are most often stay in which store, like how long, so that it can arrange business suitably, and also augmented and virtual realities. So mathematically speaking, as I alluded to a moment ago, this type of problem can be modeled by the so-called multi-dimensional assignment problem, whereby we have multiple layers of node, and in this particular figure is 6-dimensional assignment problem. And in general, we say that there are m+1 layers of frames of nodes. So individual person that appeared in the previous slides would amounts to one node. And what we want to do is we want to construct groupings, and each grouping consists of n+1 nodes, with each node belong to, for example, ik belong to the case layer together with their corresponding arcs. So the arc connecting nodes in adjacent layers. And for each grouping, there is an associated cost depending on the entire grouping. For example, we will give a particular cost to this entire grouping. It need not to be simply some cost associated with independent arcs and sum them up together. If that's the case, then it's an easier problem than the problem we are treating here. So our goal is to find M grouping, where in this case, M is the number of objects in each frame, such that each node belongs to one and only one grouping. And our goal is to minimize the cost, the sum of costs of all groupings. Is it clear? Okay. So we apply approximation in value space method for this problem. As you have seen a moment ago, the state for this problem is a partial solution where xk would amount to u0, u1 until uk minus 1. And we would like to match frame by frame. What we do here is we do one-step look-ahead minimization, by which I mean we construct matchings or we select UK one frame at a time. But in addition to that, we also perform truncated rollout, by which I mean to select the control UK here, we construct some tentative matchings starting from the next frame by using some base heuristic, and then apply certain cost function approximation with structures that matching the assignment problem. It will be clear a moment later. So essentially what happened is, let's say, to select the matchings between frame K and frame K plus 1, what we do is we construct a cost matrix between all the arcs of those two frames. In particular, let's say this particular arc, we assign the cost, that is the cost of this entire grouping. So the constructed tail portion of the problem would facilitate the value we assign. We facilitate the design of this arc cost. And because of this special cost structure, what is nice about it is that when we do selection of UK, the Q factor minimization reduced to solving a two-dimensional assignment problem. Recall that I said a moment ago that we have a truncated horizon and we construct tentative solutions starting from the next frame for the tail portion with certain fixed lengths. And this, once this is done, this part have construct some tentative solution, then this particular arc, we would assign the cost that equals to the cost of this entire grouping. So it's not anymore a cost that only relate to similarity or overlapping between those two frames, but similarity in a way between this tentative trajectory and the trajectory we have constructed until this stage. And the effect is, by taking into account the truncated constructed tail portion, even though it's tentative, we only use base heuristic to construct it. And once this matching is done, this part is gonna break, and we're gonna extend this truncated matching and in order to solve this new matching again. So once you construct this purple, like finish the control selection UK, we move on to the next frame and start to go to this stage, and XK and UK become XK plus 1. So this purple broken line would become red. Suppose this is the final solution, and repeat, and so on and so forth. And the effect of taking into account this future frames and in order to facilitate the control selection for the current stage results in robust and consistent matching against occlusion. So let's look at an benchmark study. And you can just staring at this gentleman, which using base heuristic, he's assigned with number 17. And over the frame, and you can see after a while, it was blocked by this family. And when he re-emerged, he become a new person. The algorithm consider him 41. Even obviously, everyone can see, okay, this is the same guy. But because typically for what is known as online algorithm, they only deal with one incoming frame, and comparing the similarity between a JSON frame and this incoming frame in order to do the matching. And in some rare cases, they also use the historical frame, but they don't use the future frame in the same way we do. So clearly, in this case, it fails. Now let's look at our method, approximation in value space. It's still 16. Okay, let's pause at this moment. So what is going on under the hood is, in several future frames, our algorithm would use this base heuristic and construct the path of the same gentleman. And this constructed tentative path in the future would be used to facilitate the the matching decision at the immediate next time instance. So because, now moment of truth, because of this long-term memory, when just at this moment, you already see in the future, there is this old gentleman look incredibly similar to this person I see in the previous frame. And it decides, okay, this is the same person. And that is what is going on under the hood. And if we go back to this illustration here, at this critical moment, the future constructed trajectory inform, okay, despite the occlusion that happened in the previous frame and so on, it can kind of connect the dot in between the frames that happen during occlusion. So this is why intuitively it results in this consistent and robust matching outcome. Yes, please.
So this, I assume, isn't being run online at the exact same frame, right? Like it needs some future frames in order.
Yes, precisely. That is correct.
But if this guy were to reemerge post the lab
Yes,
for long enough that it's longer than the lab, then you would.
that's precisely correct. So there's, I mean, there's a limit that our algorithm can stand. For example, just as you said, if this gentleman happened to be just walking almost aligned with another person for long enough and beyond the truncated rollout horizon, and there's nothing we can do about it. And it's true, this category of method typically are known as batch method, and this every incoming frame and you match it, this is the online scheme. It's known as online method, and our method is called typically categorized as batched method. And what is typically known in literature is the batch information is sort of passed through certain neural network to deal with all together, instead of, in our case, using the dynamic programming formulation and approximation in value space, we still treat frame by frame, despite that we have the entire batch information. And it's true, for example, in our experiment, let's say the truncated rollout is, the window is 8 frames, then we are 8 frames behind the real time compared with this online method. Yes?
So, like, essentially run at just 8 frames behind.
Yes, so for example, if we go back to this illustration, after this control selection is finished, at the end of truncated horizon, there would be a new frame coming in. Then we deal with this frame and still have 8 more frames for us to run truncated rollout. So that is how the method is working. Yes? Well, that's correct. So this is a simplification of what is going on. And in reality, it's certainly not all the time. It's symmetric and there are objects coming in and coming out. And we typically maintain under the hood certain frames. And if this object never reappeared, or if all the object that is present that are nowhere near similar in measured by our feature vector, then we delete it. So there are a lot of technical like implementation details under the hood, and Patricia in the audience is one who actually do the heavy lifting. So if you want to know more about it.
Yeah, symmetric matching. Symmetric matching, and the ones that are not matched are just kept for a while and then they leave it. They don't find it. Because they could be entering the team, right?
But when you see this kind of something to it, and the same thing, you maintain the admissibility of the base.
Sorry?
How do you maintain the admissibility of your base?
Okay, that's a very interesting question. And in fact, what happened is the method are in the spirit of rollout, but it's not identical to rollout in the sense that we lost the hope of having all the nice properties of cost improvement and so on and so forth. And that's mainly because one thing is this is a truncated version, so it's not loyal, like faithful reproduction of the exact version of rollout. That's the first thing. And second thing is, even though I'm saying that once we construct the tentative tail portion, we have this grouping cost, and this grouping cost, for example, this group would assign to this arg and so on. But this grouping cost involve a lot of heuristics and testing and so on. And in reality, we don't really know what is the right group cost for a particular matching. So I guess this is what we say as guided intuition. We are guided by theory, but the application is more involving a lot of other complications that we just deal with in by heuristics, essentially.
So to do traditional rollout, as you understand it, you have to have some sort of expert that can tell you, oh, this video, this mapping of bounding boxes and IDs is better than this one. So that's kind of difficult.
All right. Any other questions? Okay, that conclude today's lecture.
Yeah, like Jameson said, there is no clean closed form cost function here. It's just buried in some software that we can calculate its value, but we can't visualize exactly its computation, its forms, analytical form. So the implementation poses a lot of challenges. It's covered in your class notes under the term roll out with an expert, okay? When the expert is the one that evaluates, that provides values for a cost function. And incidentally, let me also recognize Kadusha Sunuru, who is the prime mover of this study, and he's here in the master's thesis right now, and she knows a lot about the implementation details. So you may ask her questions about things that that sort of complicated and that other people have done. Actually, traditionally relied on software and implementations that were already available, and download the software and use part of the software and so on.
Yeah, that's it.
To inspire the cool project. That was the whole point of this.
Okay, next time we hope to have another type of application, which is also at the forefront, has to do with transformers, ChatGPT kind of stuff. And we're still working on it. And hopefully we can be done by next Tuesday, next Wednesday, and be able to give you a lecture on that. It will be in time, because it's going to be, next week's lecture is going to be the last lecture before the spring break. And remember that we have a deadline at the end of spring break, provide a proposal for your term paper. So we thought we'd give you as much information as possible to motivate you to get started with thinking about the term paper.